Good morning, good afternoon, good day, everybody. My name's Sam Fernald. I'll give an introductory presentation for about 8 minutes about our Transboundary Groundwater Resilience Network of Networks, a project funded by National Science Foundation with some of the great collaborators you see at the bottom of the screen. And this is our annual workshop. We'll start with just a brief introduction and then have some great participatory activities. Our network is established as part of this ExcelNet program funded by National Science Foundation. And the goals are to accelerate the process of scientific discovery and prepare the next generation of US researchers for multi-team international collaborations. And we have an issue that needs this type of collaboration of networks. It's unprecedented transboundary groundwater depletion. These systems along borders of groundwater have particularly complex issues that are causing unsustainable use, extraction in excess of recharge. And our approach is to understand the complexity and how it can be addressed within these 4 key areas that we're converging: interconnected hydrologic and social systems using data and system science advances. So this logo with the 4 pieces, we're bringing those together within this kind of one effort for catalyzing transboundary groundwater resilience research. And we're connecting existing networks. We are identifying the capabilities of this convergence approach to basically determine what are the key questions, what are the key gaps that need to be addressed. Long effort to basically, we just heard in a different presentation yesterday, 1,900 different international treaties have not really helped with transboundary groundwater depletion. Extensive hydrologic studies on their own are not addressing depletion that negatively impacts people, communities, ecosystems, economies. So we're trying to identify these gaps and also support the development of the people who can do the research, students, early career researchers, and the people within these different networks of water data, systems, social science, who can work to address these issues. And we really feel that we need this network approach to create new synergies for innovation that haven't been addressed. We have heard from stakeholders what we addressed the Water and Climate Coalition with an activity coordinated by the World Meteorological Organization, and heard that there's a real need to add human system understanding to hydrologic system understanding. And we would like to bring these efforts together and actually make some meaningful progress. So here's just a little bit more detail of one example on the US-Mexico border. There's a river coming into a system of an aquifer that's shared across the US-Mexico border. That's the Rio Grande. Due to climate change and drought and increased use, there's significantly less surface water coming into the system. So people are extracting more groundwater, and that's on both sides of the border. Research has shown that the recharge, water going back into the aquifer, is occurring in the US side, not in Mexico. The complexity of human and hydrologic interactions occurs within each country and across the border. And the problem is the individual water user response to less incoming river water is to pump more groundwater, but that's maladaptation because it pulls the rug out from under the system. It basically exacerbates scarcity. So we need resilient adaptation, bringing together technology, changing use patterns, better legal and better community involvement in defining solutions that are not going to basically make the situation worse. Some of our discoveries, what we need, this was highlighted at our Water and Climate Coalition activity with sites around the world. Mexico, South Africa, other places where we need these simple, shareable water and society transboundary models that allow communities to be involved and understand the key drivers in these systems. What are the key parameters that can be impacted by the actions of the communities involved? And our project is addressing this need. Another great discovery, Ilya was the lead on this and found that visual network analysis showed clusters of work in transboundary groundwater are disconnected. You see about 100 little clusters of people publishing together when you look at all the published papers in this topic, but they're not networked together. They're not bringing the power of all of that work to bear on the issue. So we have some activities that you can participate in right now. There's the link or the QR code at the bottom here. Just for an example, we've had some amazing seminar series. You can learn about that. Collective learning meetings where the focus is on students and early career researchers. And you can definitely engage in our network of networks, sign up. I'm getting toward the end of my allotted time. So thank you very much for your attention. So happy you're here. And I'm going to hand it over to Christine Tang for the transition.
Hello, everybody. Thank you so much for attending. We appreciate everyone who chose to share their time and knowledge by coming here and trying to make a systems map with us. We would like to please be inclusive, respectful, and help create a safe space for all community members to feel empowered and included. And if there's anything that happens that concerns you during this workshop, please email me or Jeanette Torres. Our emails are on this slide. And now I'll hand it over to Jeff and Kat for the systems introduction.
All right, so I'm Jefferson, and also Kat will be helping me, and we'll be leading the systems mapping workshop. So just a very quick introduction to systems thinking and systems mapping, which is what we'll be doing today. So what is systems thinking? I'm sure a lot of you probably have heard of this term. Everything is connected to everything, especially when we're dealing with complex problems. Yeah, so now it's no longer just sufficient to break down phenomena into isolated parts and try to understand what's happening through a very linear cause and effect thinking, right? It's no longer just about how A causes B, it's also how B comes back around and affects A, and thereby creating circularities and nonlinearities. So this actually calls for a shift in mindset from analytical thinking to systems thinking. So systems thinking, very briefly, calls for a holistic approach to understanding phenomena. We seek to understand the whole and the parts at the same time by studying the complex interrelationships between system components. So here we're trying to understand how everything is connected to everything and how phenomena emerge from the synergetic as well as the competing interactions between different system parts. So why systems thinking? Here, a lot of times when we're dealing with dynamic complex problems, we want to get a deeper understanding of all the interrelationships in the structure of the system that are between different components. And then we try to perceive how these interrelationships or interconnections give rise to problematic system behavior. So here we have sort of the behavior over time graph. So a lot of times when we're dealing with something, for example, here, groundwater, you kind of, what we're looking at is really how it develops over time. And with systems thinking, we want to kind of map out all these structural reasons for what's causing this observed behavior. And by mapping out the system, we can identify high leverage policy levers for systems change, as well as to better mitigate policy resistance. By policy resistance, what I mean is a lot of times when we intervene in one part of the system, you can't really anticipate what all the consequences will be. But with a systems understanding, you can see how a certain change in the system will go through different parts of the system and might come back around to then affect your initial change. So one of the tools for systems thinking then is systems mapping. So systems mapping is a collaborative process of building very visual representations of the systems in a causal map, or also what we call a causal loop diagram. So through this mapping activity, we can understand how a variable fits within the larger system, and also understand if and how the system influences itself. That's what we call feedback loops or feedback linkages. This helps us reveal relationships that can be quite confusing or puzzling, as well as to create a very shared understanding of the problem within the group itself. And now Kat will be taking you through like the building blocks of what you should know in order to carry out systems mapping by yourself.
Yeah, perfect. Thank you, Jeff. Yeah, so for the workshops of today and tomorrow, we're going to be building a systems map with you. So we have a lot of lovely facilitators who will help guide you through the process. But it's good that you guys have a little bit of an idea what we're going to do. So here's a bit of an introduction of what a systems map is. So really, there are two building blocks to the system map. So you either have variables or arrows connectors. So the one thing that we need to have for these variables is they have to be quantifiable, because we really want to see in a systems map is how one thing affects the other thing. So we need to know these variables need to be able to increase or decrease. So we prepared a little example for you here in the image of how these variables actually link together. So you have two different types of connectors. This could either have a positive polarity or a negative polarity. So a positive polarity basically means that if variable A increases, variable B will increase as well. So in the example we have here is groundwater recharge. If groundwater recharge increases, then groundwater storage will also increase. And with the negative polarity, it's the opposite. If variable A increases, then variable B would decrease. So you have this opposite. It could either be the other way around too. If variable A decreases, variable B would increase. So in the example here, we have groundwater withdrawal. So if groundwater withdrawal increases, the groundwater storage would decrease. And then one little note we made here is you're going to be hearing the words positive and negative a lot these 2 days. So don't think they're not the same as being good or bad, like the way we can also use these words. So when we say positive and negative, we really refer to these polarities. So really what we're going to do with systems mapping is we're going to be making hopefully a lot of feedback loops with you guys. Yeah, like the feedback loops, as Jeff said, we're looking for circularity in these systems maps. So that's really what we're going to do. So the same as these links, the whole loops can have a polarity as well. So this could either be a positive polarity that we will also call reinforcing, or a balancing polarity, a negative polarity, which we call a balancing feedback loop. So we have two feedback loops here as an example for you. This is just to show you guys the concept of what these loops are. It's a very simplified version of a systems map. So what we're going to be building actually these couple of weeks, these couple of days will be a lot bigger than here. So here on the left side, we have a reinforcing loop going from production to profit. So if production increases, we can assume that profit also increases. And then if profit increases, the managers can be very happy and they can decide, oh, for next year, we're going to increase the production. So with a delay, this production then increases. So you have this dashed lines is what represents the delay in that loop. So what a reinforcing loop does is the initial change is amplified. So we had that initial change of production increases, and then as we go through the loop via profit, production increases even more. So that behavior is amplified. Then with the negative feedback loop, the initial change is actually counteracted. So if we walk through this example, starting at the top with water withdrawal, you have water withdrawal. So if you have an increase in water withdrawal, groundwater storage will decrease. If you have groundwater storage that decreases, water availability will also decrease. And if water availability decreases, production decreases. And if production decreases, the water withdrawal for the next time round will decrease. So we started this loop with an increase in water withdrawal, and we ended up, when we closed the loop, with a decrease in water withdrawal. So this is really, what's behind the negative, or a balancing. That's in the word, like it balances out. A balancing feedback loop. So one other thing to mention here is you see that both loops go through production. In a lot of complex systems, you have a lot of loops that kind of interact and that kind of share many variables. So in this situation, you kind of have two competing loops. Like on the one hand, you have this reinforcing profit loop. So they, if the managers are happy and if profit is coming in, you just want to produce more and more. But then this loop eventually will be restricted by the water availability. So what really, this is going a little bit more into systems mapping, but what would really, if it will go into a little bit more systems modeling, when we would measure the actual change, it would depend on how strong each loop is. But for now, I guess it's enough for you guys to know that you can have a loop that has this reinforcing behavior, and that can then be restricted by a balancing loop. And then a little bonus, stock and flows. We're not in the systems mapping activity. We're not going to distinguish between what is a stock variable and what is not a stock variable. So yes, but we wanted to mention, because it's an interesting insight in how system dynamics works. Stocks are really points of accumulation in a system. So what makes a stock accumulate is a flow over time. So in this example here, you have groundwater storage as our stock, and then what's going into this is groundwater recharge, and what's going out of it is groundwater withdrawal. So if the outflow is bigger than the inflow, over time the stock will decrease. And the other way around, if the inflow is bigger than the outflow, if the groundwater recharge is bigger than the groundwater withdrawal, you have a stock that's accumulating over time. So these flows that you see here, they're always a certain change over time. So for example, here you could have a change of this many liters per year, and then your stock is just your groundwater storage in liters. So yeah, dynamic problems tend to be stock variables such as groundwater, or another example of a stock variable could be greenhouse gases in the atmosphere, for example. But as I said before, in the systems mapping activity that we're going to do today and tomorrow, we will not be distinguishing stock and flow. Don't worry, we'll just be using variables and connectors, and the facilitators will help you through every step of the process So Jeff will now tell you a little bit more about the plan for today and tomorrow.
Okay, yeah, so today and tomorrow, the task now is to get you into groups where you collaboratively will build a systems map. So what will the problem be we'll be looking at? It's related to what Sam has already presented, it's TGR's problem. It's one of the main issues now is unprecedented transboundary groundwater depletion. So we kind of, this network has the overall research question of understanding why transboundary groundwater depletion is happening and how it can be reversed. So yeah, and I heard that most of you here are hydrologists as well. And so you already kind of have a existing knowledge about what is actually happening. And you'll probably realize it's very complex. So today, our task now is to get all your mental models of the system and put it down onto a map and then do it as a group so that you can also collaboratively expand on parts where you are uncertain about as well, based on other people's expertise. So the plan will be facilitating systems mapping in breakout rooms, and you'll be asked to join a group shortly. And for each room, there will be a facilitator that is assigned to guide you. And the goal is for you to identify and map the system drivers of transboundary groundwater systems, and also for us to see if there's any agenda setting that can be done for transboundary groundwater resiliency research. So for the rest of the time, we will be we'll be working in our groups, and we will carry on tomorrow when we come back at 9 a.m. Mountain Time. So there is actually no need to come back to the main room. So at 11 a.m. Mountain Time, you can actually leave and then join us back again at 9 a.m. tomorrow. Yeah, so I think now Jeanette will be setting up the breakout rooms so that we can put you into each room appropriately.